units in one apartment, they have a common hot water system. And the energy uses or the gas supply for hot water system, what they have done is they have one system, but for each unit, they have meter. So they can note down the readings for each and every unit, and accordingly they bill them. That's only the solution. Otherwise, maybe in future some new artificial intelligence approach will develop, looking the number of phases in the home. You never know. This technology is developing a lot. Time. So at this moment, there is no other solution other than otherwise, other than providing meters. So, okay. Any other question or suggestion? Not only the question, but any suggestion based on your experience.
The collective usage or the collective rates is less.
Yes.
That is that maybe that's why they started with this concept. I think.
Okay. Any other question or suggestion? Or anything which you have faced or felt about where you're living or okay. So the next part which was to basically design the system for that area. So first of all, we looked where we are going to provide the main pipe system, the trunk sewer system.
So, sir, one more question. So, in design of this stormwater collection tanks, distance also matters because losses also would be there, whether it's a lined, drainage system or if it is placed nearby and how long, where's the distance, then also that should also be taken into consideration. Because a lot of debris is getting thrown in stormwater collection.
So all those aspects will be taken into account in the design of the collection network. So when you have a pond, the storage tank, before that, I think in one of the slides I showed okay, you can see before this raw water storage, which is the stormwater, we have the gross pollutant traps, which we talked about. So that will remove all the initial large particles before it enters into the raw water storage. And sometimes even before that, we will have a sedimentation tank too, where the large particles will be removed before it is entering into the raw water storage. So depending upon the quality, all those modifications will be site specific. So as such, there is no one solution for everything. Okay? So that has to be taken into account. The site specific condition, the quality of that water, the storm water which we are collecting. Okay? At different points in the system, where we can have either the coarse particle removal, GPTs, gross pollutant traps. Okay. But this is how the treatment is done and supplied back to the, but as you said before, raw water storage tank, there can be a sedimentation tank, there can be gross pollutant traps at different locations, which are being cleaned on a periodical basis. someone asked about the data that has to be required for using those softwares. Because whatever your input is, the output will be according to that input. There are many, lot of information that is available in the literature. So if there is no information or data available, maybe the best point will be to see where in the literature, locally or from overseas, relevant information can be collected. And we all are facing the similar issues of difficulties. We collect some information, we look for literature, and we refer in our studies or documentation or reports that literature. Over time, that information can be generated. There are supporting agencies to provide funding because data collection is a very expensive exercise. Like for example, we want to study the end-use application. End-use application means that in a house, how much water is being used for toilet flushing, how much water is used for garden watering, how much for kitchen, how much for laundry. So you have to provide meters for each and every point. So you know how much water, total water coming in the house, then how much water is being used.
Same problem, sir.
Electrical appliances, I think it is much easier.
Yeah.
Because those meters you can provide, yeah. But with the water supply, I think you need the meters, which you can record. And number of studies they have been conducted, and there are reports available using putting meters in number of houses together, 30, 40 houses, and use a study. If you want to share, if you want to know a little bit more, then I can share a report with you. I can show you from where you can download number of reports which may be of your interest. Before I finish today's lecture, I will show you that website. So there was a Urban Water Security Research Alliance research program in Queensland, where different universities and CSIRO, where I was working before, we were partners for that study. And under that, there are maybe 25 to 30 technical reports, which are available for everyone to access. It is freely available. And those reports, technical reports, are associated with the stormwater quality and use applications. So there are a number of reports available. I will show you the website, and you can see which is of your interest. You can download from there. And they are quite detailed in description. They were approved by the experts. You will see 10, 15 reports which my team at that time they documented, and those reports are available. But there are so many other reports available too.
In which website?
I will show you. Before I finish today's lecture, I will show you the website from where you can download. You can see number of reports. Okay, so that's one in Queensland, Urban Water Security Research Alliance. There is another study that was conducted by Boyda Research Institute in Adelaide, and they have put all those reports, and you will see 5, 6 reports on water sediment design on that website, which you can also download. Okay, there is a report on conducting the social research, and there are so many other reports which you can see, and you can download any of those reports, which will help you in your studies and also for getting information. So I will share those 2 sites with you, and I will show you how to access those sites, okay? Okay, so the next part for us was to see how much material will be used in providing those services. One, the reason was that we want to conduct life cycle assessment. And for that, we were looking for how much will be the embedded energy in manufacturing that infrastructure, whether it is a pipe for water supply, whether it is a pipe system for sewer network, or whether it is a pipe system for the stormwater collection or the third part. Okay? So that was one aspect. We want to know how much material, how many kilograms of material will be used. The another aspect was that we want to conduct the life cycle costing. Then we want to see what type of material, pipe sizes, how much is the cost associated with those pipe sizes, and that includes up to the laying of those pipe sizes. So we conducted the conceptual, we developed a conceptual design, and for that we first looked where we are going to provide the water network. And then what we did was, then we provided number of residential units load on those nodes at different points, because otherwise it was not possible to use the software and design in detail, because that is very time-consuming process. That will only be done when we have decided what option we are going to consider, and then we go for a detailed design option. Okay? So we designed the network transceiver based on the load, based on the population which we transferred at different nodes, and we got the sizes of those pipes using simple local guidelines. Okay. So they specified, okay, for per kilometer, the head loss should be 2 to 3 meters per kilometer. Using that information, we conducted the sizing using either Hazel-Williams equation or Darcy-Weisbach equation, and we developed those basic design. There is a book which you can see over there, The Optimal Design of Water Distribution Network. That is a part of my PhD thesis, which I did from here with Professor P.K. Swamy, and both of us, based on my research component and based on what we did after I finished my PhD, so we published that book. So I will leave this book with the university so that others can also use it. This is being used in many parts of the world. And Tehran University, they translated this book into Persian for their application. So we use simple equations for finding the pi parameters, and then after that for each and every, we developed different blocks, and the block sizes were 940 meters to roughly around 450 meters, and we arranged those houses, and from each pipe was supplying for both sides of the houses. Okay. So this way, we developed those blocks, and we put those blocks in the trunk pipe network so that we can cover the whole area. So for example, you can see there were 4 residential units where residential blocks were attached with this node, supplying water. Okay. So that way we designed this network, and ultimately what we found was that there were total 40 residential blocks, and each having 720 allotment homes. Okay. Similarly, we did for industrial and commercial areas. So this way, this is the design of the network, supply network, but we also designed the plumbing system for residential units, residential houses. Because we wanted to see the total infrastructure that is needed for providing water supply net system. And why plumbing was important? Because there was in some option, say for example, option A, where we have only the reticulation system, water is available, only the potable water supply available for all the applications. So we have one plumbing system there. But the moment we have alternative sources of third pipe network, where we have recycled water for a specific application, then we have two plumbing systems within the houses. So that's why we designed plumbing systems also to get the idea of the total material that is going to be used in the water supply system or the wastewater system. Same thing we did for wastewater. So this was the size of that one single lot or the allotment of the land or the block. We designed that, conceptually designed that, okay, what is going to be the roof area, the land for for garden and all those, and where the kitchen will be, where the water closet will be, bath. So we conceptually designed based on some of the already available information local. Okay. So based on that, we designed the plumbing networks to get that information. So there are guidelines available for designing the plumbing network. Okay. So based on that, what we found is that in different water servicing options, we talked about 4 options. How much, what is the total length of the pipe that has been used? How much is the weight of different type of pipe material which we used in those? So you can see up to what extent we did the analysis. And then based on that, we calculate, because each and every type of pipe will have different energy required for their manufacturing process. Their cost will be different. So for LCA and LC's life cycle costing, that helped us in finding out the cost and also the energy required in manufacturing those pipes. So we did the same thing for all these options scenarios. Okay. As you can see in option D, there is a significant reduction in the, because there was mostly the plumbing part. In case of option D, there was no major network system, but it has increased, the total length has increased because the internal plumbing was separate for rainwater tanks, separate for grey water application, and separate for the wastewater. So that's where the length has increased in comparison to, you can see with option A, but the size of the pipe was smaller. Okay, so that's why you can see the total weight is significantly less in comparison to other options. Because size was small, but the length was much more. Okay. So that way we calculated the total length, their sizes, and also the weight. Okay. And we did the same analysis or design for wastewater. We did the same design for stormwater. So we got all that information about all the 3 type of systems. Then what we did was that in providing services, how much energy will be required? Based on the topography, based on the size of the pipes, okay, based on the treatment requirement. And because in one option we were treating stormwater, in one option we were treating wastewater. the requirements for the treatment were different. We calculated, and also we need some terminal pressure. So the terminal pressure, as we know, when we have water at home, it comes with a certain pressure. Okay. Over in Australia, the minimum pressure requirement is 20 meters. So each and every home should have minimum pressure of 20 meters. Because some of the appliances which we use, they work only if we meet the pressure required. Okay. So there are a number of factors which are dependent on the energy requirement, the terminal pressure requirement, topography, type of development, nature and extent of the treatment, water supply sources from where the water is getting, and also where it is being disposed of. And there can be some other local factors too. Similarly, the chemical requirement will be the nature of treatment, raw water quality, and wastewater characteristics. Because we need chemical for water treatment. Similarly, we need certain processes for stormwater treatment. And also, we have to have disinfection, chlorination, as we are supplying treated wastewater back to the home. So all that quantity that was calculated. The life cycle assessment was based on the flows, because that was basically the sizing and also the how much quantity being reused, contaminant loads, pipe material, and other pipes in different infrastructure provisions. So energy uses, chemical use. So all that data, I think Sigma Pro is a one software, if I'm not wrong, that was used for this study. I think when you will get that report, you can see much more information, which is a very significant amount of data is required for those software. So there are certain groups, those have much more information about the data. We are working with them to conduct this LCA for us. So the water utility hired not only us, but another group was very specialized in LCA, but most of the infrastructure, water quality, water usage data was provided based on our study to them. So the system boundary for LCA, we look for raw material extraction from the mining, material and manufacturing process, use of water technologies, then we put in the houses, then capital works, infrastructure, everything is included into the LCA assessment, life cycle assessment. That includes the energy requirement and every aspect of the energy and material requirement. So based on the data which we generated through this study, we looked into the LCA aspect, and you can see this, the top part of those parts. This is the infrastructure part, which is the embedded energy in the infrastructure. So we conducted two similar studies for two different areas. And what we found was that whatsoever option we consider, and the time required in conducting LCA is very significant, because the data requirement, the information, what we found is, based on this study and that helped us getting this publication, was that it was around 10 to 12%. Okay. So that information helped in further studies for not conducting LCA, because the two studies which we conducted, we got the similar results that the embedded energy requirement is roughly around 10 to 12%. That was one major outcome from the studies. And then you can see the reticulation system, the energy required, then you can see the wastewater operation. So each and every aspect we separated, and then we got how much is the overall LCA, the greenhouse gas emissions related in CO2 form, equivalent. The interesting part, what you can see over here is the scenario A, which is using conventional centralized approaches, we are getting minimum amount of greenhouse gas emissions. Then it will start increasing. In option B, we are using wastewater recycling. In C, it was stormwater recycling. And this scenario D was where we are using the self-contained option. It was quite high because we were needing energy in providing rainwater supply. There was a pump pressure in the rainwater supply. It was not by gravity because we need a minimum pressure to supply. Then we were treating grey water, we were treating wastewater. Okay, so because of the energy requirement was significantly high. So we got that information from there. So we compare different options for global warming, eutrophication, water usage, and solid waste generation. The solid waste generated was high in scenario D, which was self-contained, because in each and every home, there was a sludge which was being generated in the wastewater, which was to be removed periodically. Then we did the costing. Again, interestingly, you can see the scenario A, which is a self-contained, the centralized system. The cost of the system was minimal. Then the cost increased significantly high in self-sustained systems because each and every unit has their own system for water supply, for wastewater. Okay. And there was few systems associated with each and every one. So the another thing which you can see over here, this diagram, I can see in this diagram, this is not giving a very good picture, is that the local concept that was contributing the same amount in almost all the options, because local council was more responsible for managing the stormwater network system, the municipality. The water utility was responsible for providing water wastewater services. So over here, the contribution was quite significantly high, similar in this case and similar in this case, but it reduced significantly less in case of self-sustained system, because all that cost for all that infrastructure, for grey water system, for rainwater tank system, for wastewater treatment options, so the system, it was the landowner, the owner of that house, that he was contributing. So that means there was a shift from utility cost to the consumer. That was another disadvantage of having self-sustained units. But when we looked not only the life cycle cost, but also the environmental cost, and we termed it as a community cost, the total cost. what we found was that the scenario A was not the best option because we were using significantly more water, imported water. We generating more greenhouse, we're providing more nutrients to the bay. So because of those reasons, we found that this was not environmentally sustainable option. These type of studies may not be suitable for each and every reason, but that local utility was interested in looking the overall environmental cost, because that will be the cost to the community. It is not at the cost of the capital or the infrastructure, but how much it's going to cost to the community. That is including the environmental cost. So based on this study, initially they decided to go for option B. Sorry. So, but they finally decided to go for an option where they can have the stormwater treatment locally because the state provided some funding for stormwater harvesting. But this analysis gave them some idea that it is essential to include the community cost rather than just looking one aspect, that is the life cycle cost. So this whole report is available for sharing. There is a publication based on this study. Happy to share. I think I emailed to you, shared with everyone. So that study, that publication is the summary of what I have described. But you will get more information in that report, which we will be sharing. I think Dr. Sharma just started giving some information today. Okay, so this is what I want to share with you today. I can briefly go through that report. And before that, I will share two sites which I was talking about, where there is a number of reports which are where they are available. You can download from there. So I will open those sites so that you can note it down and you can take a screen photo. So I will show you those sites.
Just one thing, how do you overcome the foul smell coming out from this treatment? Normally they have the smell problem when there's a local treatment plant.
Yeah.
Maybe fine to adopt scenario C or D, but it has some disadvantages also.
With scenario B, where you're using stormwater, I don't think there will be an issue.
But with the wastewater.
But scenarios, but if there are issues with the smell, and that's why they try to locate those treatment plants where it has a minimal impact. They have some means to collect, that is basically they put the hood over the treatment plant and they get that all the gases coming out. So they use, based on the complaint from the community, they adopt certain means to reduce or minimize that impact. But yes, there can be some issues with that. But some of the modern treatment plants, they have very minimal impact because of that.